Hello everyone, let's start the new section. A second typical application of Biot-Savart law to solve the magnetic field is a circular current loop. The figure shows a circular loop of radius r carrying a current I. Let us calculate the magnetic field B and point P. On the axis, a distance x from the center of the loop. Select any current element IDL on the loop. The angle between the current element IDL and the vector r is 90 degrees. From the Biot-Savart law, we know that the vector dB for this element is at right angles to the plane formed by IDL and r, and thus lies at right angle to r, and the figure shows. The magnitude of dB is also given by the Biot-Savart law. R can be expressed in terms of x and r, the distance from the center of the loop to the point P, by geometrical relationship. We consider a diametrically opposite current elements indicated in the figure produce a field dB prime symmetric to dB. The magnetic field vector contribution generated by all current elements on the ring at point P is shown in the figure, forming a symmetric conical surface which has the same included angles theta with the x-axis, the same exponent dBx, and the components perpendicular to the x-axis cancelled each other out to zero. Therefore, the total magnetic field at point P is a red arrow vector shown in the figure. The components of the magnetic field perpendicular to the x-axis is 0. We can therefore replace the vector integral over all dB with a scalar integral over the parallel components only. The magnetic of the field is given. Let the angle between dB and the x-axis be theta. Cosine theta can also be expressed in the terms of x and r by geometrical relationship. Note that I, r, and x have the same values for all current elements. Integrating this equation along the loop, we obtain total field B. The direction of the field is determined by the right-hand rule. Grasp the wire in the right hand with the thumb in the direction of the current, and the fingers curl in the direction of the magnetic field. Now, let's discuss some special examples. When the point P is at the center of the circle, where x is equal to 0, substitute it into the above expression to get its maximum value. For a tightly wound cones of the n identical circular loops, the total field is n times this value. When the current flows not a complete circle, but an arc of a circle, we can obtain a more general result. Suppose the arc subtends an angle phi at its center, then the integral gives not the full circumference of the circle, but only the arc length r times phi. The field at the center of the arc is obtained by multiplying phi over 2 pi. Based on these two basic models, let's consider a slightly more complex example. As shown in the figure, 2 thread wire 1 and 3, and a 3/4 arc 2 forms a current carrying loop. The direction of the current I is shown in the figure. Now, to find the magnetic field at point O. Since O is on the extension of the street wire 1, the contribution of wire 1 to the field O points is 0. The arc angle phi of arc 2 is equal to the 3/2 of pi, and it produces a field of B2. The direction of B2 is perpendicular to the screen outward. For point O, B3 is a field generated by the semi-infinite straight wire 3, and the direction is also point outward. So, the total magnetic field at point O is the sum of these three quantities. If the distance x is much greater than radius r, so that the point close to the loop are not considered, the r in the denominator is omitted. The expression of the field B reduced to this form. Multiplying the numerator and the denominator by pi, where s is equal to pi times 2r squared, is the area of the circular coil. This dependence of the field on the inverse cube of the distance reminds us of the electric field of an electric dipole. It's often convenient to consider a loop of wire to be a magnetic dipole. Set N to be the positive normal of the current carrying circular coil. The magnetic moment of the circular coil is defined as a vector Pm, whose magnitude is a product of the current I and the area S, and the direction is the same as the direction of N. The formula of magnetic moment is applicable to any shape of coil. Thus, we obtain the vector expression for the magnetic field produced by the magnetic dipole only if the area S of the coil current is small, or if the field point is far from the current. Can the loop current be called a magnetic dipole? A third typical application of Beasics law to solve magnetic fields is current carrying solenoid. In the previous discussion, we have one way to obtain the uniform magnetic field. We could create a device with two flat plates carrying equal current in opposite direction, where the fields would reinforce in the region between the plates and cancel outside the plates. A more practical way to obtain a nearly uniform magnetic field is to use a solenoid. As indicated in figure, a solenoid is a helical winding on a cylindrical coil. The wire carry a current I and are wound tightly together so that there are n windings per unit length along the solenoid. Let's calculate the field along the central axis of the solenoid using our previous result for the magnetic field of a circular loop of wire. The calculation of field of the axis is difficult using the Beasics law, but in the next section, we discuss a different and much easier way to calculate the field of axis. The figure shows the geometry for calculating the field on the axis. The current in the up part of the solenoid is out of screen, and the one in the lower part is into the screen, and the dotted line in the middle represents the symmetric axis. The radius is r. We wish to find the field at point P. We assume that the windings are so narrow that each can be considered as approximately a circular loop of where the number of turns per unit length is n. Consider a thin ring of the width dl. The number of turns in that ring is n dl, and so the total current di prime carried by the ring is in dl, since each turn carries current I. R is position vector from current element to point P. L is the position of the ring relative to the point P. The field and P due to this ring is dB. The direction is right along the axis of the symmetry. From our previous results for the circular loop of where we write the magnetic field dB along the central axis of the solenoid. The variable L is expressed as the angle beta, which is the angle between the position vector from point P to the current element in dl and the axis of the symmetry. From the right triangle shows in the figure, we get the geometric relationship between I and theta and R and beta. Substitute them into the expression of dB. Then dB becomes a function of the angle beta. To find the total field due to all such rings, we integrate the expression from beta 1 at the left end to beta 2 at the right end. Evaluating the integral, we obtain the expression, which gives us the magnetic field on the axis of the solenoid at the point P is valid for point inside and well and outside the solenoid. The direction of the field is determined as euro using the right-hand rule, so that if the current is circulating counterclockwise as field from right, the field is horizontal to the right. For an ideal long solenoid, the length L is much greater than the radius R. In this case, beta 1 approaches to pi, beta 2 approaches to 0. The expression becomes very simple. It gives us the field of an ideal solenoid and all interior points off axis as well as on axis, and the field is 0 at all points outside the interior of the solenoid. If the point P is at one end of the solenoid, the current carrying solenoid is semi-infinite. In this case, beta 1 approaches half pi, beta 2 approaches 0. So, the field B becomes half of the case of infinite length. The solenoid is a relatively simple device capable of producing a magnetic field that is approximately uniform. In this solenoid, the field is nearly uniform if the radius is much compared with the length and if we are not too close to ends. That's all for the section. Thank you for your attention.